Okay. I fixed the collector, so I think I will talk about that now. It's much cleaner now, and it actually works as you want. So let's see. So this is the program that we want to compile. So it has a main function, and it has another function. The main function has two variables, var1 and var2, and then it overrides into var1 later. And the other function has three variables, none of them overlapping, so we should see two basically 2 places on the stack for this function and 3 places on the stack for this function. Yeah, so let's see it. Make. So if you look at the main, we can see 8 times 2 is 16, so that's correct. And the other one is 8 times 3, which is 24, also correct. So let's look at the first one. I still haven't fixed the bug where it says 0 for some reason. I don't know why. Yeah. And it's only for the first one. So if I remove, yeah, basically if I write anything else here, it's still 0. I don't know why. But the first one writes into -8, which is correct. The next one writes into -16 because they're 2 different variables. And then the next one should write into -8 again. And as you can see, it does it, so we are happy. And for the other one, 3 spots, -8, -16, -24. Yeah, so that's very nice. I can just show you the symbol collector. So I thought about this a whole bunch. If you remember from the last video, I talked about using the token descriptor for basically kind of a, not really a hash value, but maybe like something to index into to identify it with, because they should all be unique. But as I showed in the last video, you can actually have these 2 tokens are actually different because they are on different lines or different column count. Yeah, so I had to find some other solution for it. Then I went over, should I maybe just copy the entire array so I have 2 of these? But it seems quite stupid to do that. I even tried to implement it. It was just horrible garbage, basically. So while I was brushing my teeth, I thought of a better solution, which was to just have a pointer. It's just a struct. Let's see here. This is the whole thing. So this is my symbol buffer. It's an array containing a struct with a char pointer and an integer. This int is the offset from the stack, so this number, but it's actually, it's not 8, it's just a 1, because you have to multiply it by 8 because I use 64-bit. If I use 32, I had to multiply it by 4, so yeah, whatever. And then there's a char pointer. Yeah, so that made it much easier, and I had already made this function from from the Alexa. I just didn't remember it because, yeah, you know how it goes when you're dealing with a problem. You might not, you have dug yourself so far in a hole that you can't even see out of it, but then you just have to take a step back, look at it again, and yeah, then you realize how stupid your other solution was. Yeah, so you can see here I made some notes for myself, and this was the Eureka moment. Yeah. Yep. So yeah, I can show you how it works. So the basic idea is we want to iterate over each of these functions to figure out where we should store each of these variables. So we can do that because I have a buffer based in the parser. It's here, and I know how big it is. It's 20 bytes, so I can easily iterate through them all. Do we even do this here? Loop begin collect. Oh yeah, I just use a descriptor. Yeah, whatever. Yeah, it works. So I just iterate through them, and then I get the function, so I can visit the function. And two things we want to fill out in this function are, let's see, where have you? We have the variable count and the symbol table. So this is a offset. It's not a pointer, it's just a descriptor, and an offset into the symbol table. And this is how many variables there are in the function. So we want to set those, and as you can see here, I set the symbol table at the start because for the first function the offset is 0, so I will just set it now, because then later I can update how far the actual offset into this symbol table we are, which is denoted by this offset variable here. Yeah, so that's the goal. We want to fill those two fields out. So we visit the function. We don't need that anymore. Let me just delete everything. Nice. So we get the function, the first function. We have the descriptor for the function because we calculated it up here from the RBX. It's just an integer. First it's 0, then it's 1, then it's 2, 3, 4, 5. Yeah. We first get the function. Then we look at the body of the function. Is it just a single assignment or is it a statement list? If it's just a single assignment, just call the assignment function and then we return, and we are glad. However, if it's a statement list, if there are more than one statement in this function, as there is for this main function, there's actually 3 statements. Then we first pull out the statement, and we first look at the left hand side, and then we check, is this an assignment? If it is an assignment, then we skip this jump because it's not equal to this. So we call the assignment function, which is this one. We just this one, and the other. After we have checked the left side, then we need to check the right side, which we get from these two. So we can pop them here from this call, right? And then we just check again, is it a statement list? If it is, then we need to jump up here again and then do the same again. However, if it's just a normal assignment, then we can do the assignment. So let's see what the assignment actually needs to check. So yes, this is still relevant. Okay, so what we do is we retrieve the assignment. So the identifier, we want the name for it, which we get here, and then we call a set offset on stack method, which is defined down here. And this is where all the magic happens. If you read this comment, we can use the fact that the locate symbol returns an empty spot if it doesn't exist in the table. This is really useful. I know you do it a lot in other languages, where just either you get the result or you get an empty spot where you can fill it out. So yeah, that's basically the idea. So I call that function, which is defined up here, and that basically once it loops through this array where it first finds the identifier, so this var1, and then it looks at the first entry and does a string compare call, this one, which basically checks if two strings are equal. If it is, then we don't do anything because, well, okay, the locate symbol just returns one of these structs, or if there are none, it will just return an empty spot, so basically just past the end of this. So we look at this char pointer. If they are a match, we return it. If we get to the end, and how do we know if we get to the end? For some reason, assembly is just filling my buffers out with 0, so these buffers, they are just filled out with 0. I don't know if it's supposed to do that, but I'm I'm using it, so I can just check if this is 0. Then we know, because it's basically the same as a void pointer. A void pointer is just defined as a 0 in C, for example. So if it's a 0, we just return it, and then we have a spot. We return the address just after this. So that's basically what we're doing. So we first get the symbol table, and we get the string we want to match against, which in this case is var1, and then we just loop through it. So we can see here, RDI stores the variable, RSI, so the name var1, RSI is the symbol buffer, or the offset into this. And the first 8 byte is the pointer, and then the next 4 is the offset. And important here, if the RSI, which we get from here, so we dereference rex, which stores the symbol buffer, and this is RSI is the char. This is wrong. Rex stores the symbol buffer. RSI stores the stored char pointer in the buffer. Alright, so if it's 0, if it's a void pointer, then we know that it's an empty spot. So we check, is this 0? And then we just return the empty spot, which is the address of rex, or the address that rex stores. If it's not, then we need to check if they're equal, and because this compare string is actually modifying the RDI and RSI registers, then we need to store them. And it also zeroes out the rex register, so I store that also. Then we just compare, are they equal? Then we have located the symbol. Otherwise, we add 12 to rex, and that is because our struct is 12 bytes long. So the first 8 bytes are the pointer, or is the pointer, and then the next 4 is the offset. So 4 plus 8 is 12. So that's how big our struct is. So if you want to move through the array of this struct, then we need to add 12 each time. And then we just go up to the beginning and check again. Yep. So that's super easy. That's how you locate the address. So let's say we want to set the offset for this and for var1, and let's say it hasn't been inserted yet. So then currently our struct would look like this, or our what was it called, symbol buffer. It's just this. Then we locate a spot, which turns out to be here, the first empty spot. And then we check, is it an void pointer? In this case it is, because there's nothing there. If it's not, however, then it's already inserted and we can just skip it. So we already know how I fixed the problem, why I overrode the old offset. So imagine we have already set the offset for the first two variables, then we get to the second and we look, okay, we actually return the first address and it's not a void pointer, then we know it already inserted and we can just return. However, if it's not inserted, then we call increase symbol count, which is defined down here. It just loads a variable allocated on the stack, increases it, and stores the value again inside it, and it's stored up here. It's initialized to 0. Then we get here, we want to store the address of basically this point, because this is basically going to override what I have in rex. Normally in assembly, rex is the output register and RDI and RSI are input registers. So yeah, so I store the I want to retrieve the address for this token, for this char pointer. So I pop my RDI, which is basically the descriptor for this variable, and then we call a retrieve function, retrieve identifier function, which does this. So it loads the identifier tokens, and then we add the offset to it, and then into rex and output it. So now we have the address for this token, or this char token, char pointer, and then we just want to move that into the first place here. So now we have a struct which looks like this. So it's some char pointer. We don't know what it is. It only in runtime you know what it is, but right now you don't know what it is. You just know we have filled it out with a char pointer here, right? And then we want to get the symbol count, which we increased from 0 to 1 here, and that leaves a 1 in EAX, and then we just move it offset at 8 bytes, which are the first 8 bytes. So we write it in here, and then it's going to say 1. And then basically it's just going to do that for the second one. So var2 first, we look at this. Is var1 and var2 equal? No, they differ by this character. So we return false. Then we check the next. Okay. How is there anything stored here? No, there's not. So we know this is an empty spot, and we know the symbol is not located inside the symbol buffer. Then we can do this part again. This part, which basically inserts a new one. So now we insert a new char pointer, and we increase the symbol count, and we insert it here, offset by 8, so 2, right? So let's now imagine that we get to this var1, then it would actually first look at this, and it would actually recognize, oh, this is already here, so this is not 0. Because it's not 0, it contains a pointer. Then we just leave because we don't want to do anything. Okay, so now this symbol, this is done now. So now we can move on to the next. So I have made an offset that basically points here past the end, so we always know where to start. And that's basically what this method does. Set symbol table. It loads the current symbol offset and moves it. Let's see, it's down here, and moves it into the function. We load the function buffer, and then we count how many or how long we need to go in, multiply by 20 from RDI or EDI. So that's the descriptor for it, multiplied by 20. So that's the index into the buffer, the function buffer. We know it's 20 long, so we need to multiply by 20. So that's the offset. And then we can just move the current offset into it, which is offset 16. And how do we know that? Because that is how I have defined it here. So 0 plus 4 plus 4 again, that's 8, plus 4 again, that's 12, plus 4, 16. Nice. Yeah, so that's basically it. Super clean implementation, I think. It's not that... Okay, so now we know that at least it has a runtime of O of n, where n is basically the... it's actually the total length of this times the number of variables. So the runtime for this function is n times number of variables or symbols. So the total length in the... Okay, so this is all for each function. So the total length of each symbol in this function times the total number of symbols in this function. So it's... yeah, it's okay, I guess. It would be much better if I used a hash map, but I don't feel like implementing a hash map in assembly. I could probably do it, but yeah, fuck that. Yeah. So that's it. Now I just need to actually make it pass these trees correctly, and I need to, or the binary operations, and I also need, because right now we have a right to left derivation instead of left to right, which is basically how you count or how you do math, or how humans want to do math. We want to first evaluate this and then add it to the right side. So if we had like, if this was the what we wanted to do, so 1 plus 2 plus 3, and we first wanted to add these two together and then add it together with this. However, right now I have it such that it first adds this two and then it adds that to this, and that's not necessarily correct. Like imagine you have something where the order actually matters. For example, this. Right? Shouldn't that should matter, right? Or maybe this. No, this is hard. Okay, so this can be two different things. It can either be one. It can either be 1 minus 2 minus 3, which is 1 minus 1, which is 0, or it can be 1 minus 2 minus 3, which is -1 minus 3, which is -4. Right, so you see there's a difference. Yeah, so basically I want the first one, or the second one. But right now I do this. Yep. I don't think it will be difficult to fix it. But I will do that maybe tomorrow or some other day. I don't know yet. But anyways, I'm kind of proud. We can also see here. Alright, so first we push the 0. Let's just change this to 0. First we push the 0, then we push 3 and 2, then we pop the first two, these two, and then we basically do it. Right, so here we can actually see the problem. It first subtracts 2 from 3, so we get 1, and then it pushes that to the stack, and then it pops those 2, and then it adds them together, so we get 1 here. That's wrong. Well, it's not wrong. If this wasn't 0, then yeah, whatever. You know what I mean. Here you can actually see that I'm parsing it incorrectly. Yeah, so that's basically all I had for today. Very nice, very nice. Goodbye. See you next time, maybe.